Hi, welcome back to AP Chemistry. We're still in Unit 4, Thermochemistry, and this is podcast 4.5. We're going to look at some more applications of Hess's law that maybe you didn't get to work with last year, or maybe you did. Let's find out. So what we know about Hess's law is this. Basically, we know that the enthalpy of a reaction is a state function. So if a reaction is carried out in a series of steps, then delta H for the reaction will equal the sum of the individual steps. So all you have to do is find out each little step along the way, and you'll know what your overall delta H is. This provides a useful way of calculating energy changes for reactions that would be really hard to measure directly, like combustion reactions. Say, you can't stick a thermometer in the fire. That's just way too hot and not very safe. So here's what we could do. Suppose that we have, where's my reaction? Okay, let's see. We must have a couple of reactions going on here. So let's make a guess. First we have the reaction of nitrogen and two oxygens, and that's going to have an associated enthalpy change of 180 kilojoules. And since we started low and had to go up high, then we're going to call that positive because we gained energy in that step. And then we had a step where O2 and NO2 were combined. So I'm guessing that's what we had for products here. Making wild guesses according to what we've got. And that makes NO. And of course it's not balanced, but that gives us an idea of what's going on. This process, we're going down in energy, so we have a negative 112 kilojoules for that step. And then the next step took us from NO. That's it. That's all the steps. This is where we end up. And so the overall is going to be the sum of 180 minus 112, which is equal to 68 kilojoules. Another way of calculating that is just to know what's this and what's the end. And we do final minus initial, right? So here's our initial heat, and there's our final heat, and we subtract the two. And it's the same as finding the sum of each individual step. There. We made it, even without our balanced equations. So here's an example. We'll calculate the enthalpy change for the combustion of methane to form carbon dioxide and not water vapor, but liquid water. All right, so we are going to have to deal with two different things. First, the combustion part, and then in the next part, turning water vapor into liquid water. So we have two separate steps to consider. Each of them has an associated enthalpy change. So what we do is find the sum. I'm going to add these reactions together. So we get gaseous water cancels away, right? 2 and 2, that just goes away. And now here's this. So what do we do with our heat? If I added the reactions together, then the heat is just the sum of negative 802 plus negative 88. So add those up. We should have negative 890 kilojoules. That's it. That's how we do it. That doesn't seem so bad, huh? Of course not, because I always start off with the easy ones. All right, example 2. The enthalpy of combustion of carbon to carbon dioxide is given by this value, negative 393.5 kilojoules for every 1 mole. And the enthalpy of combustion of carbon monoxide to carbon dioxide is negative 283 kilojoules per mole. All right, so we have our two separate reactions. Here's carbon to carbon dioxide, then here's carbon monoxide to carbon dioxide. All right, using this data, let's come up with the enthalpy of combustion for a related reaction where we're combining carbon with oxygen to get carbon dioxide. All right, so we want carbon, solid carbon on the left. We've got it. And we need CO on the right. And right now, it's on the wrong side. So we're going to have to flip that equation around. All right, let me get rid of some scribble in here. So we're going to turn this reaction around so I can get carbon monoxide on the other side. So I'm going to end up with CO plus 1/2 O2, and then over here is my CO2. All right, so that is all gone. Now when I change the reaction around, I have to change the sign. So I have positive 283 kilojoules per reaction, right? So now CO2's cancel. CO doesn't have anything to cancel, and I have 1/2 O2. I have 1 O2s. So I can get rid of half of my O2, but that still leaves me with the other half still there. Now let's add the two reactions together, and we should get our target. So what I'm left with is carbon plus 1/2 O2, and everything else is all crossed out. All right, on the other side, CO, and nothing else is left. All right, now let's do the same for delta H. I added my reactions, so now let's add the delta H, but keep in mind we got to add the ones that we kept. So negative 393.5 plus positive 283.0. Watch your signs when you're doing this. My delta H then, negative 393.5. Okay, yeah, pushing the wrong buttons again. Gotta teach humility somehow, don't I? I'll make the mistakes, and that way you guys won't have to. I get a negative 110.5 kilojoules for the combustion of solid carbon to form carbon monoxide. So there you go. We found two related reactions, and we're able to combine them to get the one that we didn't know. Hey, that's it for this podcast. How about that? You guys are already done, so I will let you practice more in class, and see you next time.